Hello, everyone. Thanks for inviting me to give this talk in the free restriction online workshop. Today, I would like to talk about my research on the Pointwise Weyl Laws for the Schrödinger operators with singular potentials. This is a joint work with Xiaoqi Huang at Johns Hopkins University. We are interested in the Schrödinger operator on the compact manifolds, HV, equal to the minus Laplacian Beltrami operator plus the potential function Vx. Here, our potential is assumed to be real valued, and also we assume it satisfies the Kato class condition. The Kato class condition is defined as follows. Here, the integrals is taken on a small ball with radius delta on the manifold. Here, dgyx is the Riemannian distance. And the integrals, this integrals uniformly in x goes to 0 as delta goes to 0. And our Wn is just the fundamental solution of the Laplacian equation. Moreover, you may see that our Kato class is a subset of the integrable function, and it contains LP if P is greater than n/2 by Holder's inequality. The reason why we assume that we satisfy the Kato class condition is that this kind of Schrödinger operator will be self-adjoint and bounded from below. And if our manifold is compact, the spectrum will be discrete, and the eigenfunctions are continuous by the hit kernel estimate. And then we can have, by spectral theorem, we can have the HV is has a discrete spectrum with increasing order, and we can find eigenfunction e tau k in a domain, satisfying this eigenvalue equation. And we may assume that our eigenfunctions are in L2 and satisfy L2 normalized condition, which means that L2 norm is equal to 1 for all tau k. And using the hit kernel estimates by Li and Yao and Stum, we can have the following. This hit kernel estimates also give us L infinity bounds for eigenfunction, for example. And we may weaken the conditions a little bit because we just need to assume the negative part of potential is in Kato. And the positive part will not affect our kernel estimate. And recall that we have the following classical sharp Weyl law. Here, n0 lambda is just the number of eigenvalues that's equal to lambda. And you can see that in this Weyl law, the main term, the leading term is lambda to the n, with coefficients depend on the manifold. And the error term is lambda to the n minus 1, which is lower than the leading term. And this error term is sharp in the sense that it cannot be improved on the wrong sphere. And this Weyl laws is known first by Weyl and later proved by Leviton and Evan Kumovic, and generalized by Homander to the pseudo-differential operator. which correspond to the smooth potential. And indeed, one can prove a stronger form of the Weyl law, that is the Pointwise Weyl law. If we denote the P0 equal to the square root of H0 and PV equal to the square root of HV, and the indicator on this closed interval minus lambda to lambda is denoted by 1 sub lambda tau, and we write their kernels in this form. And because our eigenfunction are L2 normalized, so if we take integral in x, this is just n0 in the last page, because this is just a number of eigenvalues that's equal to lambda. So we can have the following Pointwise Weyl law. And the leading term is also lambda to the n, and the error term is lambda to the n minus 1. This estimate is uniformly in x, so we can, if we take integral on both sides on the manifold, this implies our sharp Weyl law. So it is stronger than the sharp Weyl law. And the error term is also sharp on the round sphere. And then we want to consider a similar problem for our Schrödinger operator HV. Recently, my collaborator, Xiaoqi Huang and Chris Salk, in 2019, they proved that under the Kato class condition, the following sharp Weyl law of the same form as the standard Laplacian Beltrami operator, this Weyl law still holds. And the error term is sharp on the ground sphere. Later, last year, Frank and Sabin, they proved some refinements. Also, they consider the three-dimensional, they proved some refinements in three-dimensional case, and they also consider the Pointwise Weyl law. And for higher dimension, for general dimension, it is the Pointwise Weyl law is still unknown. And that is the main topic we are interested in this talk. So first of all, I would like to introduce our first theorem. This theorem tells us that if V is in Kato class, then we can have the following Pointwise Weyl law. That is the kernel estimates for 1 lambda PV. And the error term is little o lambda to the n. We can see that if we compare this one with our classical Pointwise Weyl law, the only difference is the error term. And indeed, in 3 dimensions, Frank and Sabin already proved this under the same condition, that V is in Kato. And they also show that the error term, little o lambda to the 3, cannot be improved by a positive power, because they can find and construct a potential V in the Kato class such that the error term is about lambda to the 3 minus eta for some eta greater than 0. So we believe that our error term little o lambda to the n is also sharp in general dimension n, in the sense that we can find some potential function in the Kato class such that the error term is about lambda to the n minus eta. Our second result is called the sharp Pointwise Weyl law. Here we have a sharp here because our error term is sharp. Our error term is lambda to the n-1 power. Our condition is V is in Ln. And this Ln, of course, is a subset of the Kato class. So under this stronger condition, we can have a sharp error term. And the sharpness means that it is sharp on the round sphere. For smooth V, this is just because our HV is just the pseudo differential operator, so it follows directly from Homander's result. Last year, Frank and Sevin also proved the same sharp Pointwise While Law in 3 dimensions, and their estimates holds under a different condition, different from us, because our condition is Ln, but their condition looks similar to the Kato class condition, but is stronger than the Kato class condition. This condition, by Holder's inequality, we can see that if V is in LQ for Q greater than 3, this condition is satisfied. And we may see that here in 3 dimension, L3 is very special here. Because if Q is less than 3, then the sharp Pointwise While Law can fail. So L3 is the critical space for the sharp Pointwise While Law. And we also believe that the Ln is also critical in general, for general n-dimensional manifold. So Ln, we believe that Ln is critical, the critical space for the sharp Pointwise While Law. And the following examples may be helpful to prove this condition is critical, and also prove it can be used to prove the error term little o lambda to the n is also sharp. But currently, we have not figured out how to prove this sharpness in general dimension. And recall that it has been used in Frank and Sevin's paper to prove the sharpness in n equal to 3. But it is unknown for other dimensions. And clearly this V is in Kato class, and also it belongs to LQ for Q less than n. So it is reasonable to believe that our Ln space is critical for the sharp Pointwise While Law. Our main approach is using the wave kernel methods and the Fourier analysis. We first rewrite our indicator function 1 lambda as the following form. Here we need to use the wave kernel. Here we can expand the wave kernel using the spectral theorem. And then to analyze the wave kernel, we need to use the Duhamel's principle. We can use the Duhamel principle to rewrite our kernel. We can see that the difference of the 2 wave kernel cosine TPV and the classical wave kernel cosine TP0 is actually this explicit integral, and we will estimate this sum precisely in order to estimate their kernel. And we will use the several useful lemmas in our paper. The first one is the kernel estimates for pseudo-differential operator. And we may find these results in the book of Salk or in the harmonic analysis book by Stein. So if M satisfies this condition, it looks like if we take derivatives and in T, then it will have a decay, additional decay. And also this M, we know that if M satisfies the condition, we know that MP0 is a pseudo-differential operator of order mu. And the kernel satisfies the estimate. And you can see that if mu is -2, it looks similar to our, here we have a typo. Here this is dg to the -1. Okay. And this is related to our kernel estimate for the in the Pointwise While Law. Okay. And next we will use the spectral projection bounds for the classical Laplacian operator. By this result is due to Salk in 1988. This is the L2 to LP bound, and this result is also sharp. It is sharp on any manifold. And the following eigenfunction estimates also follows from the hit kernel estimate by Li, Yao, and Stu. And we will also use this frequently in our paper. Here we need to assume that V is in Kato. And finally, I will mention some remarks. First of all, the proof of Frank and Savin's their three-dimensional results extends the methods by Averkumovic, and their methods relies on Tauberian theorems and parametric estimates. And we don't know how to adapt their approach to handle the general n-dimensional manifolds. But they can use their, the advantage of their methods is that they can use this to prove the sharpness of their error term, and their condition is also critical. And we hope to prove the sharp Pointwise While Law for HV under some different condition, because we already proved that if we satisfy Ln, then the sharp Pointwise While Law holds. But maybe it is, we can find some conditions similar to the condition in the Frank and Savin's paper, such that the Pointwise While Law still holds. And their condition will be similar to the Kato class, but stronger than the Kato class. And this is work in preparation with my collaborator. Also, it is interesting to improve the sharp Pointwise While Law under some additional curvature condition on the manifold. So for example, if the manifold has non-positive curvature, it is possible that we can have some improvement on the error term in the While Law. This is also a work in progress with my collaborator. The last one, an open problem, is that it is interesting to consider the While Law on the manifolds on the compact manifolds with boundary. For example, the domain in Rn, a compact domain in Rn. And we are not sure how to extend the following our methods to the manifolds with boundary. And we may continue to work on this in the future. Okay. Thank you for listening.